All right, so here we have a graph. We're first going to convert this to a planar graph. So the way we'll do that is we'll create vertices here. And I guess we have 5, 6, 7 of them. So we'll just label them here. So notice that each region in this map we're creating a vertex for. And then we're going to connect any two that touch. So A touches B, C, and D. It means we'll go ahead and position them like this. E touches B, C, D, F, and G. And notice if we would do this, the lines are crossing over, and that's fair, that's fine in a typical graph, but in a planar graph, we're looking for avoiding all intersections. So that's going to be really difficult to do the way we have them arranged. What I'm going to do is kind of position them more or less where they're located in the graph. We're going to try this again. So this will be A, B, C, D, E, F, G. And we'll do the same thing, except now you'll notice it'll be a lot easier. Again, our goal is to connect any two regions that are bordering. C is bordering these. But we also want to make sure that none of our lines intersect. And almost got it there. E and E are touching. Okay, I think we have it there. And then after this, we want to determine the chromatic number. Chromatic, and let's call this, let's call this whole graph H. So we want the chromatic number of H, and the way that you'll see this in symbols is that chi is the Greek letter, and then H. So the chromatic number of H, all that means is the fewest the fewest number of colors we could color this graph with so that no two neighbors would be the same color. For example, if I start by coloring this blue, then I just want to make sure that B, C, and D, none of them can be blue. So how many colors would it take? Well, clearly I could do it in 7 colors. I could just color every vertex a different color. But the chromatic number is asking, what's the fewest color? Pretend these colors are extremely expensive and you're trying to minimize costs here. Well, one way to do it is to look for look for complete graphs, and specifically let's look for a triangle. Okay, here's a triangle. This is also known as K3. In other words, it's 3 vertices that are all connected to each other. What happens in a complete, even if it's just like part of a graph, it's a subgraph, you have to use a different color for each 3 of these. If I use blue for this and green for this, C has to be a different color because all three are touching each other, so they have to be different ones. And then at this point, the question is, could I continue and use only 3 colors for the rest of the graph? Notice I haven't really made any choices yet because these 3 had to have some color, and specifically they had to have different colors. So it didn't really matter which color we used. We had to use up 3 colors for these, but could we continue now? Well, D, if I'm going to try to do this whole graph with 3 colors, I'm going to have to color that one green because it can't be blue or red. It's touching both blue and red. And E, notice it's touching B and C, so it's already doing red and green. I need to pull that into a third color. F here is touching green and blue, so if we're going to color this whole graph in 3 colors, we better do this red. And then G, we do it in green. It would have been impossible to do this graph in any less because Again, because even our starting three, but we had that situation several other times. There was a triangle ACD, CDE, DEF, F. There were lots of triangles in there, so there's no way of getting this with two colors. Um, and that means the chromatic number of this is 3. It's the fewest possible colors we could use to color this whole graph. Now, one of the interesting thing about planar graphs is here H is a planar graph. What the four-color map theorem tells us is you take any map, like drawn like this, where you just have the regions in any shape or whatever, and you convert it um, to a planar graph, you'll be able to color that planar graph with no more than four colors. The chromatic number cannot be higher than four. Sometimes you get it even less, like we did here, but you'll never go through this process of creating a map into a planar graph, and it takes more than four colors. Now, if you just have a general graph, let's take K5. So K5 is just 5 vertices, and K stands for complete. Um, there we go. So notice two things. First of all, because each of these five are touching another one, or touching all of the others, you have to use five colors here. So the chromatic number K5 is actually 5. So why why does this break the rule here that we set that we can always color it in four or less? It's because K5 is not planar, and there's no way you can draw it. There's no way you can draw this graph in a way that the lines don't intersect. You can untangle it a bit more than we have here, but you'll never avoid at least two of your edges intersecting. Unlike what we have up here with H, because H came from map. If it comes from a map, it'll always be possible to do it in four or less. But if it doesn't come from a map, I mean, it could take any number of colors. The chromatic number um, of K10, for example, is 10. Like a complete graph, it'll always be whatever number that is, because you can't draw it without these intersections.